Yes, so that's the idea. And the idea, let's pitch the idea in a slightly different way. I look at this slide that you may have seen, the HSP curve, number of residues aligned, percentage sequence identity. In the blue region are pairs of proteins that naturally evolved and have similar 3D structure. If they have similar 3D structure, they have similar secondary structure. Right? Now let's just pick a point here. The green arrow here happens to be if I have 100 residues aligned, if 33 of these are identical, then essentially the two have the similar 3D structure, hence secondary structure. Okay? Turn that around. 67 residues can change in 100. We still have secondary structure maintained. Okay, assume you went into the lab, you took 100 residue protein and you changed 10 residues. What do you believe will happen to the structure? Will it be the same?
Depends on the structure, because
that depends on the structure.
We had this, I think, this chameleon sequences and stuff.
Depends on the structure, and but I'm not talking about 10 consecutive or 11 consecutive chameleon. I'm just saying I give you randomly to pick 10 in 100, and what do you believe is the most likely outcome of that experiment? Yes, it depends on the structure, it depends on what you change. This is all true. But actually, surprisingly, most of your changes, both the one chosen at random and the one chosen with intelligence, are going to lead to proteins that do not fold. Okay, now we have a puzzle, right? So implicitly that means that I cannot change 10. Well, if I do the chameleon sequence as an optimization process where they played around with this until they found the 11. But the first 11 they picked didn't work. And again, so there was a longer story behind that for the Kim work. But how come I cannot change 10, or the probability that when I change 10 is that I disrupt something, while in nature we see 67 changed?
Well, because nature, I would argue, on average, does not, well, there is a selective pressure, which is kind of random, but the genetic, so the selective pressure actually is the difference. When we do something at random, there is no selective pressure behind it, but when nature does something at random, selective pressure facilitates that only viable genotypes stay in the gene pool.
And it's important that you understand this part. So the point is, nature randomly picking 10 is not doing better than I. But selection means you will not see those. The 10 that don't work, you will not see. You will see only the ones that essentially keep structure the same, because they will do the same function, or even do somehow optimize something, but typically the ones that are neutral, okay? And these are extremely unlikely, and the only reason why those are the ones we see is because otherwise they wouldn't survive. Okay, you have these, me going into the lab trying 10, this is what nature does all the time, and they die. We don't see them. What we see is what worked, okay? That means now, we go a step further. That means that, and this brings us back to what you said, Franziska, the particular type of exchanges you have revealed something about which family, which protein, about the details of that structure. What you can change where depends on the structure. It depends on where you change, okay? So back to this HA3 family here, some columns are more conserved than others. You cannot just randomly change anywhere. So if you see this alignment, you immediately know, well, don't choose your 10 where the purple is, right? This is already clear. When there are columns that are conserved, you're not going to hit those. That's your first lesson to learn. If you had to randomly choose 10, take it outside of those, right? Now, this somehow, I'd like to visualize those most conserved ones here. And there is this one here on the structure sits here. The first one sits on the structure here. So this is not 3D view. It's two different sides of the same molecule. What I want to illustrate is that in 3D, you have two parts close in 3D that in terms of sequence from here to here are relatively far away. Now, if we took out a window, a sliding window of, say, 5 residues, shown by this black box here, that in those 5, I see actually what I can observe in those 5 is influenced by what sits here, what sits far away from the 5. So in the 5, I have some implicit view of something that happens far away. So the information, what this one looks like, is not explicitly in the 5. But how I can change the 5, if that were a salt bridge, if that would be a positive charge and that a negative charge, then I will not observe in the alignment here a lot of negative charges around it. It needs to be positive, or the other way around, right? So meaning, in that window of 5, what you can observe is constrained by what is sitting close in space, possibly far away in sequence. Now, that implies that there is sort of information in this window of 5 about something that is outside of the window of 5. In the analogy, this is like the raindrop in which you see the world, right? This is a reflection. In some sense, you see in this profile a reflection of a process that happens elsewhere. And implicitly, it means that you sort of convert a problem that is relatively difficult to solve. So find the correct solution depends on the initial conditions. Tiny changes will either get it here or here, and that may be wrong. You convert that type of chaos problem to a simple problem where tiny changes in the initial condition get to the same solution by, if you want, averaging over different species. Okay? So that means then that we sort of go from the level of the simple vector, where we have 21 input units per 13 times 21, and each one of these 21, one is 1 and all the others are 0, you get into a probability, where the probability really that goes into this one now, simply that is your sequence, your query sequence. Those are 4 proteins that are part of the same family. So you do pairwise alignment, you find they're all similar enough above some threshold, and then you simply count frequency. You count how often in that family do you see a D, P, E, so and so forth and so on. And now, rather than having a vector with 21 units, 1 is 1, all are 0, you simply put in these probabilities. Nothing else changes. Right? In order to do that, of course, what you have to do is you have to sort of build up a pipeline in which you begin with a sequence, search against the database, find the family, build up a profile, then sort of decide what is above and below the line. So above the line, you know, they have similar 3D structures, which may be the E value of 10 minus 3, and maybe this HSP value. You extract the alignment, you put the alignment into the machinery, right? Now, so far, all these devices that I talked about, machine learning devices, they only use the same type of information that a Gore method, that a simple probability table would use, essentially sequence. Now we upped it. We brought in the profile. What else could you put in? In the machine learning device, now we are free to add additional features, to add additional information. What else could we possibly put in? What could we try? Can you throw some ideas at me? Actually, let's put it differently. I'd like everybody in the group to come up with one idea.
Cell location, where in the cell?
Where in the cell, subcellular localization. I believe that's a good idea. Historically, we have never done it because when people began developing secondary structure prediction methods, they were not available. So today we would actually have them available, at least through prediction, and we could try that. Yes, I believe that would be a great idea. Next idea. We can go around, or let's just go around because we start with Gary.
I have no idea.
This one is not counting. Think about it. Just jump in whenever you have an idea. You're going to have one at some point.
Maybe we can look at genes up and or downstream of the gene of the protein to look for
operon. But why wouldn't chaperones?
I'm thinking about it might be possible because that ties into.
Okay, that could be. This information is not easily available. So subcellular localization have much more of these. So most of those will not be next to a chaperone. So most of it will be 0. But this is something we can try. Is a valid statement. Yeah.
Like, for example, charge of amino acids?
So we could look at the charge. So we could say, okay, let me go back one here. So part of the input is essentially this 21 vector, where now we have profiles. But then I put for each amino acid another unit that says positive or negative charge or something. Okay? And that, in fact, has worked. We have used that. Next idea. So, yeah?
Like other biochemical properties like
Expansion of the same idea. Yes, we use another sort of set, hydrophobicity, size. So there are a couple of things that come to mind and that actually do help. Now, say you looked up biophysical features, and one way of finding is you suddenly find a paper that has 160 different indices that you can use. Would that work? Would that be a viable solution here?
It sounds like overkill.
Yes, it sounds like overkill. The real problem is then essentially what you do is you have 21 that comes from the amino acid or from the alignment, and you have 169 that sort of process this information. So most of the information that you, literally most units will code something that is sort of a derivative of what you put in the first place. To focus on charge, on size, on hydrophobicity, on a few others does make a lot of sense, because I named now 4. So 4 in 20, that is sort of an okay ratio, but 160 in 20 is not. And in fact, that certainly doesn't work. We tried it. Next idea. You're off the hook.
Or just use function, like if it's a channel or if it's
That's a great idea, where again, this is a great idea. In fact, we have not tried that one. We have also not tried that one. And historically, we have not tried those because historically they came later. So that we have a large set of proteins for which we know some ideas about function. And typically now that we sort of predict binding sites, that we know that something is a channel, that we know where it's located, we use secondary structure predictions for those as input. So now to use those back into secondary structure, we could do that, and possibly so there's some advantage to coupling things, and the subset localization one is one that I clearly considered the first. But yes, that is an idea, another idea.
Tissue?
Tissue. Yeah, that's a great idea, actually. The problem then is the coding. We have 170.
That's the same problem with it.
No, I would shy away from that. But wait a minute. No. Because that is one unit. So this may be ballpark, but it's not as bad as the other one, because in this particular case it's 170 units that you add to the whole thing, not 13 times 170. So it's not that bad. In fact, it's so typically today this window here is 25 residues. So this solution is 25 times less bad than using all indices. And this is something, right? So it's not this. It's more than an order. It's almost 2 orders of magnitude better. So that could actually work. And so since the numbers here today 25 times ballpark times 21, you see that adding another 160 is sort of within that. That could be tried. We have never tried that. So at first you have no idea. Now you one comes after the other.
It's just something like you could also mark the special amino acids, like for example cysteine, because it has this covalent binding. So if you have cysteine there, then it really makes sense to say, okay, so it's got to bind to some other.
So is that now cysteine, or do you think about others?
Cysteine proline is also, but I think that
well, 2 units I can
should definitely notice. It's more like hydrophobicity and something like that. So that you have this really special.
But it's true. But again, so if you added a cysteine, then that's 1 times 25, 1 unit for 25, right? So for each of these, you would then say it's a cysteine.
But I think it's really important because it really determines how.
So I can tell you it didn't work. Empirically, neither cysteine nor proline. At least those 2 I tried. No, I also tried the charges. They didn't work. I mean, I tried the charge idea works as a charge idea, but putting the different types of charges, because the lysine is a long side chain, that did not work in my hands, at least when I tried. Other ideas?
Do you believe that expression.
I believe anything.
That expression information could actually be helpful. I'm kind of, I don't know. It's like because
I don't know.
Be the same,
I have no clue.
Protein, the same.
I have no clue, and that's an interesting idea. With those data being available, that may help. Yes, but something simpler. Yeah.
Maybe not only counts the proteins themselves, but the neighborhood next to which they occur.
Oh, the protein's neighborhood, with the protein binding neighborhood, or what do you mean by that?
Yeah, like the direct primary structure and neighbor. So you don't only have proline, but you have, like, most of the prolines come after.
No, but this is exactly there, right? Because you put it in a window.
Yeah, but like for every amino acid, the amount of.
On that note, I love these simple rules. Prolines come after a valine, do they? This one certainly doesn't, and this one also doesn't. Anyway, yeah, but that information is there, no? I'm still not sure what you mean on top of that. Or you want to essentially have an additional 400 table where we sort of look at the pair frequencies in this, like a two. That would be an idea. So we would blow up by 400 units and look at K-mers. That may work, actually. And I certainly never tried to do the K-mer on a level of profiles. That could work. Another idea. So we have so far not at all looked at features that are sort of more global, for instance. Global features could be in this entire protein that I have. So you have asked this issue, are there prolines in this? But you have never asked, is this a proline-rich protein, right? And the window will not see that. There's no information in this window about what happens elsewhere in that protein. Okay? So you can put the overall amino acid composition. In fact, another thing that is important, you know that proteins span from 30 to 30,000 residues. Is this a long protein or is it a short protein? Is it a multi-domain protein? So if it is very, very long, any protein that has 1,000 residues or 800 residues is at least a two-domain protein. It's a multiple domain protein, right? Is that one of those, or is it actually the single domain type of 150 or 80 residues, right? Then you shift this window through the protein. Is this window that you're looking at in the neural network, you have no idea where in the protein you are. Are in the middle? Are you sort of close to the beginning? Well, you sense it when you have the spacer units all on. But after you sort of have the W half past the W half point, so if you have a window of 5, once you have hit point number 4, you will not see a difference. Nevertheless, whether there is a lot before you or not may matter. Certainly, you cannot sort of fold back into binding. So when you're predicting a strand and you're sitting somewhere in the middle, it's more likely that you have a partner if you have two sides to give than when you have only one side, right? Things like that. So the distance of the end to the N terminus, the distance to the C terminus, those are additional pieces of information. Another piece of information that in the alignment, what is very important, you know, is how many insertions do you have? Is that a place in the alignment where essentially everything is aligned? Not that is entirely conserved. But do we actually have an alignment for all the sequences in that region? So are there deletions in there? Is that a region that is conserved? Yes, you see conservation, but what you need is to put this conservation into perspective of the overall alignment. Is it conserved because the two proteins have 100% sequence identity? Or is it one of the residues conserved in two proteins that are very varied? And this is also something that you have to put in there. And this helps very, very importantly here. Now comes the next issue. I said that we can train the neural network by presenting more samples of beta strands, and by that you improve the prediction for beta strands. But the overall accuracy of that device is less, right? Now we could have two different devices, one that is sort of optimizing to get beta strands better, one is optimized to get higher overall accuracy, and these would be two gray lines here. And now in your final prediction, you're not going to give it to the user and say, well, I have one that is better for beta strand, which one do you want? Click yes or no, right? Do you want this or do you want that? No, you have to somehow come up with a solution that is answering all the questions. And one way of doing that is you average over a bunch of different devices. Now, when you have these gray lines, each of these gray lines symbolizes here one particular solution, one particular network that is trained with one particular input or one particular way. And as long as you assume that these grays have a white noise that differs. So white noise means they make mistakes that are not systematic. So it's not that they can never see helices with a particular length because somehow they never use that information. Or there are some systematic errors. As long as the mistake of these things has some aspect to it that is stochastic, by averaging over several of those, you improve. So the green line here is going to be more likely to get a higher level than any of the grays. Okay? As long as they are stochastic enough. When the grays now are really different methods, then the next issue becomes maybe one of the gray lines is so bad that putting that into the average makes it all do worse. So this is a different story. And then, you know, for sort of the more modern things, there are many other things that you can put. And this is, when I say modern, even that one here is now 17 years old. But sort of more recent signal structure prediction methods are way more complex. Let's just leave it there. I'm going to show you a prediction that, again, is over 20 years old. And for that particular protein, which is SH3, you see the sequence up here, the observed secondary structure. The blank, again, is neither E nor H. In red, the helix, and blue, the strand. This is Chow-Fassman, so single first generation method, single probability, single residue probability. Go, window, this is actually Go 3 here of the second generation. And this is sort of the device that uses the profiles as input, PhD. You may remember that the first generation is less, so the expected accuracy is sort of 50 to 55, not 59. The second is sort of maximally 55 to 60, not 65, so these are above. The question is about this one. Is that above or below? Ultimately, this number here that you quote for a prediction method, you say prediction method has, and the number that I'm going to talk about now, today the numbers are no longer that. I'll get back to that. But let's just have the number here as a placeholder. You say that the method has an accuracy of X. That does not mean, what is X is an average of a database. X is actually an average of a distribution. So you have a bunch, this is the per residue accuracy for per residue per protein. And you have a distribution of proteins. For some proteins, this number is higher. For some proteins, this number is very, very low. In fact, there are proteins here for which prediction accuracy is just above 10%. So you may immediately spot that there are 1, 2, 3 in this data set of, I can't remember, 600 or something. So you depend on how you count, but clearly there are 3 that are absolutely worse than random. Okay? So yes, you create a relatively, what was at the time the best method that was available, and yet for some proteins it was not better than random. Now, this is what you quote, the average, and visually, so I put in the sigma here. Visually, do you know how to see the sigma on the plot, right? So you have to roughly look at where's 2/3 of the data distribution, so I don't know, you put an arrow, a line here or something, and then in between is the standard variance, right? How do you get from a standard variance to the standard deviation? You don't. Okay, so we do it at some later point. But now, in the prediction here, I also show something that's called a reliability index, and I show a star. Now, the reliability index is the following idea. So the device that I showed you so far has 3 output units. And for simplicity, I'm just going to use 2. I'm just going to use the H and L. And say in one case, the prediction is 0.9 and 0.1. In another case, the prediction is 0.6 and 0.4. Again, the actual output values of the neural networks do not have to necessarily add up to 1. So here I essentially enforce by turning them into a probability. In both cases, the prediction is H, right? But you immediately see that this prediction here is stronger than that prediction. And this is what this value here means. The value, I simply scaled that difference to values between 0 and 9, where 9 is the highest possible difference. And then I put a star whenever this number here is 5 or higher. Whenever you look at the stars here, you see that wherever you have a star, the prediction is right. Okay? So, again, the star is assigned. So, in this particular case here, I know the three-dimensional structure, I know the secondary structure. But the assignment of the star does not need, so compiling this number, I need to know the structure, secondary structure. But compiling the star, or putting down the star, that is a lookup from the prediction, right? I have no information about the experimental data. It's just the difference of my values, okay? Okay, so we're back to this distribution. 72 is an average over distribution. How do you know? I give you one particular protein to run. How could you find out whether that protein is more likely to be here, or somewhere in the average? You don't know the three-dimensional structure. I give you a sequence, you use this device and you predict secondary structure. And I'm asking you, tell me how you find out where in the distribution you are.
The more stars you can compile, the more likely it's in the upper area.
Clear to everybody what you said? So essentially what you do is you do an average over this reliability index, shown here on the x-axis, and you hope that this average correlates with the overall performance, and this blue line somehow, okay, there are many exceptions, there are many red points that are off the blue and that go in wrong directions, but there is a fit. And if you sort of put two lines here, then essentially the vast majority of the data you fit into these two lines. So clearly, sorry, I don't have to go back, that clearly means that you can say tendency on which side of the curve you are. Are you going to be in the center? Are you going to be right or left? You can see that from the average reliability, so the average number of stars. And that's very, very important when you develop a method that you do this. So you have to calibrate the reliability index. So you have to first establish, is there a relation at all? Is it true that for my method, in fact, more reliable predictions are better? So more reliable is in that direction, better is in that direction. So is that direction also in that direction, right? That's one thing you have to establish. And secondly, if you can establish, we have had very few examples where that was not the case. And when you do establish that, you need to sort of really give the user a way to translate. To say, okay, from an entire protein, I get this number means. Okay? Or you can also visually put it onto a distribution. So this means you're going to be somewhere here. Or you can give a similar score, back to the idea of the star, you can do the same thing on the level of per residue. So this is the level of per protein, on the level of per residue, and the curve we look at is this one here, with the discs, the dashed line with the discs. So overall, if you predict for every single residue, then performance is 72%. It's not quite 72, it's a slightly different device here. But essentially that was the 72 from before, okay? Now you can sort of focus on the 50% most strongly predicted ones. Okay, the 50% is here. And for the 50% most strongly predicted ones, you see that the performance goes from 73 or 72 to something like 80, 83 or 84. Okay? So this is exactly what you have to give to the user, and then the user can say, well, you know, okay, I want to look only at the few where I get 90% or something like that. I want to look at the most likely to be correct predictions, and then it's important that they know both. What is most likely to correct? At least at this particular case, you max out at 90. So there's no threshold, at least in this curve, there's no threshold that allows you to find everything that is right. So when you pick the most reliable ones, you still have 10% mistakes. That's what you have to keep in mind. And you have to keep in mind that at that level, you pick only every fifth residue. Okay? So you ignore 80% of the protein. But provided the user has these two numbers, they may be extremely useful for them. Now, what is important is, another point that is important is the story of what may be called bad errors. One definition of bad errors is where you confuse alpha helix with beta strands. And what this one shows here is that even for the best prediction methods, there is very few proteins, sort of 20%, 25, 30%, only sort of 30% make zero mistakes in terms of bad. Most of them, so 100 minus 30 or 70% of all the proteins, you have at least some confusion of alpha and beta, is what this one shows. And you see some of these confusions here. And here's the story that you have talked about, is the story about the chameleon in the IgG binding domain from Kim and Burke. And essentially, so this is the sequence, this is the secondary structure of that protein, and what they realized is there was a stretch here in an alpha helix that looked in terms of sequence fairly similar to a stretch here that was a beta strand. Okay? So they took this and made up a stretch of 11 that is not exactly this and not exactly that. But these 11 here are similar to both. Okay? It happens to be that if you put these 11 into a solvent, then there's an alpha helix. But that is not really relevant. What is relevant is if you now take this peptide of 11 residues and you engineer to put it here, then actually it forms an alpha helix. If you put the same peptide here, it forms a beta strand. So now you take the same 11 residues, again they are engineered, they look similar to what is native in that sequence. At one point, the same 11 MERS helix, at the other one, it's strand. The remarkable thing about the method that I show you is the one that uses the alignment information here is labeled PhD 30. It correctly predicts it. So it predicts that this is a beta strand and that this is an alpha helix. While the one that uses no alignment, so that uses only a single amino acid sequence, sees this as a helix and that as a helix. So sees them both as a helix, which you may say is right because in solvent, whatever, that's all blah. But what I'm saying is that this original model that was used to make this slide here, in fact used 17 consecutive residues. The 11 are identical. Nevertheless, it could pick up the signal and it essentially picked it up from the alignment, right? So I'm not saying that these devices can do that all the time. This is there are 2 or 3 cases that we tried. This is the first I tried, and all of them worked so far. Again, doesn't mean they all work, but they can be remarkably successful using alignment information. Okay. Now the first, let's go into a little bit of detail. Today the number is higher. Even this slide now is outdated. Then the number was 76. Today we believe that this number is close to 80, and mostly that comes from larger alignments that we have today. But again, 76 is an average with a standard deviation, and you have to remember this because you have to find out where your protein is. Stronger predictions are more accurate. We talked about that, so that allows you to sort of guess on which side of the story you are. But now we get to the first thing. So I talked about this reliability index. I said that the strength here reflects performance. But when you sort of work out these graphs that I showed you before, when you sort of work out how a particular value in the reliability index translates to accuracy, what you do is you take the average protein. Okay? And actually it turns out that when you have alignments with not enough diversity, then the reliability index no longer is a good measure. Or the one that you calibrated here is no longer applying to that situation, because most proteins that the system was trained on actually have a lot of information in the alignment. So the few that are exceptional don't fit the bill, and this is the kind of thing that is complicated. And again, so for all methods all of these statements continue to be true. Single sequences, so not using alignment information, is much, much worse. And that continues to be true too. And here are a couple of questions. Let me just go through them. The major problem really for the accuracy of secondary structure prediction is that you get the best possible alignment. Best possible alignment means you get diversity into it and you don't make an alignment mistake. And you know that the more diversity you bring, the more mistakes you make. And there's a good trade-off between it. Whether you predict secondary structure or solvent accessibility, how much alignment mistakes you accept is very different for the two methods. I will talk about solvent accessibility later, and 2 weeks from now. And ultimately, secondary structure is sort of not that sensitive to alignment mistake as long as you bring in enough diversity, secondary structure predictions gain. Solvent accessibility predictions are very sensitive to mistakes in the alignment. So this you have to see. The question is, has the limit, so we are today roughly at 80%, is that the limit of secondary structure prediction? Well, one way of defining the limit, I talked about that briefly, is if I look at two very similar structures, so I have two proteins for which I can apply comparative modeling, how similar are they in terms of their secondary structure? That's one way of defining what's the upper limit. That's in the ballpark of 90. In that sense, we are still not there. So maybe we can push it further. Now, another question is, I said that we apply secondary structure prediction methods only for methods for proteins for which we do not know the 3D structure, for which we cannot do comparative modeling, because we don't want to compete with comparative modeling, because when we have the 3D structure, we don't need secondary structure prediction. And that is true, but you can still, the question is valid, if you build a comparative model, and then you read off the secondary structure from the comparative model, is that actually going to be better than the secondary structure prediction or worse? And it turns out, surprisingly, it's actually worse. So secondary structure prediction methods actually are more accurate in predicting secondary structure than comparative models. And knowing that has made the people who build comparative models to realize that they should use secondary structure prediction. And again, this is what we didn't believe for many years. It is unclear what the ultimate role is. Today, sort of secondary structure prediction really has become a workhorse. It has not merged into 3D prediction. Secondary structure prediction is just one of those methods that almost everything people do begins with secondary structure prediction. It's one feature that you use to predict enzymatic activity, to predict subcellular localization, to predict protein-protein interactions. You also put sort of expression arrays into this. But this is somehow one of the major workhorses in the background. Now, the problem really is, again, what is the best alignment? So you need to pick the right ones. And I believe I will go through the remaining slides a little bit faster than I had assumed. Ultimately, what this tries to answer is, how much do I, when I align against SwissProt, improve over a method that uses no alignment? And you see that the improvement of a blast is different from a profile blast, but the dynamic programming does very well too. Unclear. Now, the difference here, however, is different whether you use that e-value or that e-value. And you see that, so here we make, in those days today we make more mistakes. So today these numbers would have to be chosen lower, meaning this would have to be replaced by 10 minus 10, and this might be by 10 minus 5 or something. But ultimately the point that I want to make here is what I already said, is that sometimes here, this clearly makes mistakes, an e-value of 1. But nevertheless, the improvement is higher. This one improves more than that. It's not always the case, but for many of these values, this improvement here is higher than that one. Meaning that you benefit by diversity more than you lose by making mistakes. So here are more mistakes, but still more diversity, and that effect has a net profit. What this one shows you is that there sometimes so above the diagonal, PSI-BLAST is always better. And below the diagonal it's not, and there are points below. So it's not always better. then it is much better to use a large database here than a small database of proteins to align with. So this number, both of these numbers, 9.2 is higher than 7.6, 9.7 is higher than 8.2. So it's always helpful to use a larger database, but even for the larger database you see more mistakes. 9.7 is still larger than 9.2. So larger database is good, including more diversity is good, and I believe I'm going to leave it there. What this one shows here is, again, these are outdated slide, number of proteins aligned, the performance increase over not using alignment information. So the more you have, the better you do. And you see that those days they were relative, and the error bars here, you see that those days they were really few with 1,000 proteins. That's why the error bar is so long here. And you know that today we have many with 1,000 proteins and more in alignment. So the curve today goes higher, and the reason why the curve is constrained today is ultimately a CPU issue. So in fact that problem has become that so the default cutoff of PsyBlast is at 3,000, and the database now is so big that at 3,000 essentially you only find things that are very related, meaning that you find 3,000 and you have a very low improvement here, because ultimately you align only the same protein over and over and over again. So these are sort of all kinds of technical problems. But ultimately it means that so the larger our databases go, if we learned how to use that, the more the merrier, the better for secondary structure prediction. How do we access secondary structure prediction methods? Again, so it begins with, we need to define a standard, PDB to DSSP, then we have to define the way of using that to HEL. We need large data sets. Again, this one shows that, I believe this is, again, I said 600. This still has a sigma of 10, so it's still pretty large. Now, I said here, sort of 600 or 500 proteins are large enough to somehow show an effect. Does it mean that any 500 are good enough? No, clearly we need to sample the true distribution, so we need to somehow have a subset of what is out there. Today this 500 number is more 10,000. We clearly need to do redundancy reduction. So again, assuming a standard deviation of 10 in a Q3, if we have 2,500 effective proteins, say we have 2,500 effective proteins, again today this is about 10,000, and we had two methods here. Method 1 that has a Q3 shown here, and method 2 has a Q3 shown there. Do they differ? Again, numerically they do. This is not the question. If the author, if you were the reviewer on the paper and the author of method 1 said, I have a new method and this outperforms what exists, the closest competitor, method 2, is worse. As a reviewer, would you say this is correct? With essentially most of the data that, or some of the data that you will need in order to make that decision is on the slide. Implicitly, at least. Yeah?
No, because I don't think you can really differ between the two because of the standard deviation. Or the standard.
So what we need to do is we need to transfer the standard deviation into standard error, and this is essentially the rule of thumb, square root of the number of proteins, meaning the 10% standard deviation translate to in this particular case for 2,500 proteins to a standard error of 0.2. And it does differ. In this particular case it does actually differ. So you would argue that at least statistically significant, the difference is statistically significant, at least on the level of one standard error, right? It's not two standard errors, but it's one standard error away. Okay? You may call that borderline, but it is better. Is there something else that jumps at you? on my slide. Well, what I meant, it's a little bit misplaced here, but what clearly is not supported by this standard error are these 2 digits. So given this standard error estimate, all that they can essentially provide is the number 76.5, not 0.52. 0.52 is a misunderstanding of the situation. So they have to clearly, to be more right, have to clearly write this differently. So 70.6.5 and 76.3 and say plus minus 0.2. So again, they differ. Is that enough? Now, for answering the question, is that enough? Is there anything else we need to consider? Well, so the first question here that you should ask, when they say these 2 methods differ by that, did they really use the same data set? Did they really use the same score? Or did they look it up from a publication? And where one quotes something and the other one something else. When they use the same data set, now, how did they run method 2? Is that a web server that you run on your, or that the developer ran on their proteins? If so, what about the overlap between the one that method 2 was developed on? So ideally, you should play this on new proteins. The problem with new proteins, so in proteins that none of the 2 has used, right? The problem with that is then you suddenly get very quickly to numbers smaller than 2,500. Then you get to problems where the standard error shoots up. The standard deviation most likely is still 10. But now maybe you have 10 new proteins and you immediately see that with 10 new proteins, so square root of 10 is 3. The standard deviation of 10 divided by 3 is 3. So now you need a standard error of plus 3. So then you can no longer distinguish these 2. That's the problem. But we need to look at something like that, right? Say there are 100 new proteins, then you need a standard error of plus minus 1 at least to say that they differ. Anything else to discuss? I believe we briefly looked at this, and I'm going to go through this. So essentially what we in principle need sort of automated CASP meetings that, don't worry, I'm sliding through this. Automatic CASP meetings that sort of establish secondary structure prediction servers. Unfortunately, that no longer exists. So this somehow gives an idea about how it improved over the years. Ultimately, in between here, there's no new development. Essentially, this is most of that is that database growth and improvement of alignment methods. So secondary structure methods, without changing them, get better simply by getting larger alignments. Maybe we could do more today by putting in more information. Unclear where the limit is. Again, 90 is roughly 88 or 90 is most likely the max you can get. Maybe today we get over 80, maybe we get close to the limit. I believe the major thing that we have to do is what we can use with these methods for other aspects. Here, for instance, is one application that's already done, old by now, where they use secondary structure prediction methods to predict switches. So to predict regions where the secondary structure would switch, and that would be related to functional changes. There are many additional things that the field, I believe, needs because it's the workhorse, but the problem of the secondary structure prediction at the moment, everybody uses it, and nobody can develop new methods because you can no longer publish them. This is one of the issues. So in our lab we have developed now 3 new methods, and they have all not been published. We believe they are better. I have no slides for them, I have no publication for them, and more groups are doing the same thing. So it's more and more sort of a development that happens under the hood. But still, at some point, I believe we ought to open the can and predict not secondary structure on the HEL level, but maybe on a more complex alphabet situation, and use that for comparative modeling.